So I was gonna take a poll first. I was just on the plane, and it's really hard to sleep on the plane when you have an overnight flight. So, how many people here, like, I was just gonna figure out how people like to sleep. So, who sleeps with a neck pillow when they fly? Raise your hands. One, two. Surprisingly few. All right, two. Who sleeps? So my preferred style is head on desk. It's like bring the little desk thing down, kind of like put your head on there. It's really cramped because I'm kind of tall, but well, taller than they make the seats for. But so how many people is that? One, two, also two. So I'm assuming the rest of you guys just like don't sleep on planes or never fly. Awesome. It's like 100. Okay. Awesome. A very revealing graph of our sleeping activities collectively while flying to places far away. So, I had another one. Maybe I deleted it. Okay, well, kind of just to see what people have a background in. So who here is like used Theano or Theano? I'm not sure how to pronounce it. Decent number of people. Maybe like 20%-ish. Who's here has used TensorFlow? Also a popular one. Nice. Who here has used Cafe? Okay, how about scikit-learn? Yeah, it's very popular. I've never used scikit-learn actually, so I don't know anything about it. But okay, so who here has used Keras? Okay, so who here has used none of the above and or just like saw deep learning as like, ooh, deep learning is so cool, so hype right now. Yeah, that's why I would go to this talk too. Yeah, so I guess so in terms of why people are here, so who here is interested in NLP tasks very broadly? We may guess like 20? 20? Who here is interested in Keras? Learning a bit more about Keras? Maybe like 30? 30-ish? Who here likes heckling? Just like, yeah, keep your hands down. 0. No one here. And what is Python? I assume everyone knows what Python is. Programming language, probably. Awesome. Okay, so everyone's interested in Keras. Let's get started. Okay, so I was going to go through a little bit of the like introductory stuff. Actually, if you guys want to install this, you can go to. I have it on. Is there Wi-Fi? Okay. So I have it on GitHub, and you can download it and play with it. So there's kind of two parts to this. One part is I made a bunch of Python notebooks to kind of explain stuff, and the other part was a project that I did with like actual data, which is like I put it up in like Google Compute Engine, and hopefully if we get enough time, I was going to go through how to do that too. Personally, I think the like ideas are more interesting. So like once you have the ideas, you can kind of build on them and do whatever you want. But yeah, it's also good to see stuff practically. So if you want to go to this repository, put a little short link so you don't have to type everything out. Make it bigger? Yes. Is this good? goo.goal PEM8P5, capital P. Yeah, so probably a good idea to download it. And yeah, the README's got all the instructions for how to install it. It's basically you make a virtual environment and then install your dependencies in the virtual environment, and the dependencies are just the Keras and Theano and Jupyter. Oh, who here used Jupyter? Nice. Yeah, that is actually, I don't know, I sort of just got into it and it's pretty awesome. Oh, did everyone get it, by the way? Yeah. Okay. So, it's all aboard the deep learning hype train. Yeah. So first we can, so deep learning, like any kind of machine learning problem, is just like, how do you build a model that describes real data, right? And that's kind of something that everyone's interested in generally. And deep learning itself is kind of blowing up because there are certain problems where conventional models don't describe it very well. So the canonical examples are like vision, for example, or audio processing, because those are very highly nonlinear tasks. So by that I mean, like with vision, the thing that defines a cat is very, it's a very wide space of stuff. And because deep learning is I don't know, I might offend some people here, but it's like brain inspired. It can model things that people model well. So yeah, so it works very well. Hopefully I don't have to convince anyone that it's a good thing to invest your time learning if you're already here. And also the math is more or less the same for everything. So if you don't have any math background, I'm going to go through that a little bit right now. So the usual example for why deep learning is useful is for building a XOR function. So suppose you want, suppose you have, a graph, and you're trying to map points to like true or false, and you have a point 0, 0, 0, 1, 1, 0, 1, 1, and you want the 0, 0, and 1, 1 to be true, and the 1, 0, 0, 1 to be false, right? So in a conventional model, it's a linearly non-separable problem. So what that means is you can't draw a line through the points and have one side of the line be true and the other side of the line be false, right? So everyone following that? So for example, what's the one that's not deep learning but sort of like it? Andrew Ng. Does anyone know? No, it's the support vector machine. Sorry. So support vector machines are useful for solving linearly separable equations, and there's tricks to get around the problems of linearly separability, but in practice, linear separability it's not like support vector machines are very linear, and they're not very good at interpreting things like vision, which have like a very non-linear like subspace of like yeses and nos. Like if you have a cat from this like huge number of points, that's a very non-linear set of points. You can't just draw a line and say everything on this side's a cat, everything on the other side's a dog, or something. So yeah, so that's the motivation for deep learning. And kind of the hello world of this is to build a simple function that, or build a simple model that computes an XOR function or recognizes an XOR function, because that's a linearly non-separable or non-linearly separable. Yeah, so let's get started. First, we go ahead and import Theano and Theano.tensor, NumPy, and time for benchmarking stuff. Next, we can go ahead and define our data. So this is just what I was saying before. So x is the input variable, and y is the output variable. So you see 0, 1, 1, 0 should go to 0, false, and 0, 0, 1, 1 should go to 1, it's true. Does everyone understand kind of why that's not linearly separable, or why that would be hard for a kind of conventional machine learning problem to solve? Yeah? Cool. And feel free to ask questions anytime, by the way. I mean, I guess that's sort of a expectation, but yeah. So next we're gonna just make a randomizer, and this is kind of the crux of how do we build our machine learning model. So first we need to instantiate the weights for our model. So a basic feed-forward neural network. Has everyone heard that term before? feed-forward neural network. It means that you have your inputs, and you multiply them by a matrix, and then you add a bias vector, and then you apply a nonlinear function. So first, when you multiply by the matrix, those are kind of the neurons. The neuron activations are defined by the matrix weights, and the bias vector just means that if you feed in a vector of all zeros, you don't get zeros out. And then you apply a nonlinear function, and the nonlinear function is very important for this problem of non-separability, because without it, if you stack multiple, matrix multiplications on top of each other, that reduces to one matrix multiplication unless you have the nonlinear function, right? And I don't understand very well why nonlinear, or why different functions do what they do, but it kind of just works, magic. So here we're gonna initialize our weight matrix and our bias vector, and it's a good idea to initialize the weights with kind of random noise, and it's a good idea to initialize the bias vectors with all zeros. And so we're gonna get two matrices and two bias vectors. The first W1, B1 are gonna be our first layer of neurons, and the second one are gonna be the second layer of neurons, right? So this is kind of what it initialized to start off with. Those are the neuron activations, or the parameters of our model. Oops. Okay. So this is the heart of the network. We get output. The output of our network will be from, first we do our dot product of our input vector with the first set of weights, add our bias vector, and apply a nonlinear function. The relu function is basically, if it's less than 0, make it 0. If it's greater than 0, it's the identity function. And then once we have that output, so this will be the output of this will be a vector. We want to dot that with a new matrix, the second set of weights, add another bias vector, and then apply another nonlinear function. So the sigmoid function basically is a squashing function so that it puts everything between 0 and 1. It kind of looks like this. So that's another nonlinear function. So that's basically all there is to making a neural network. Now we've got those, we can go ahead and try to define what we're trying to learn. So in this case, we're trying to learn values for W1, B1, W2, and B2 so that the output of the matrix is close to the output that we want. This is a mean squared error for calculating the cost function. And we want to minimize the cost function. So if we minimize the cost function, it'll be close. And so we can make these updates. And the update rule that we're going to make is for each parameter, W1, W2, B1, B2, we want to change its value so that the gradient of the cost with respect to that parameter goes, it makes the cost go down. So we push it a little bit in the direction that makes it go down. Yeah, and that's how we learn. That's all there is to a neural network. So everyone, peachy keen. Yeah, so let's make Theano will make our training function and our test function. The training function has the update rule, updates equals updates, and the test function outputs our cost, so we can kind of see how well we're doing. So how close are the output values to the values that we want. So, and let's go ahead and run that, and it runs pretty well. So as you can see, the cost before training the network is maybe like 0.47, and the cost after is pretty close to 0. So it learned the model pretty well. Actually, maybe we can try like make a function to predict the input I don't know if this will work. Nope. Let's do this. No, x is a shared variable, which means it's already kind of, like, we can provide inputs. This is kind of a weird formulation for the problem. Oh well, I should have done it beforehand, but there you go. Anyway, so that's Theano. And that's how we build a neural network in Theano. So who here is this like the first time thinking about that or doing that? Nice. So how confusing was that? Very confusing. Very confusing. Fortunately, there's Keras, which is better. Yes. So Keras, I mean, Keras is maybe like an abstraction of Theano. So, like, we have our model that we just defined, a two-layer neural network that we've got all this math going on behind the scenes. I mean, I don't want to understand math because I do computer science. This is a Python conference, not a C++ conference. So Keras is going to make that a lot easier for us. And that, like, for people who are kind of into this stuff already and like, oh, Keras, I want to have more hands-on control over it. Hopefully, I'll make a good argument for why Keras, we can still have a lot of control over our models. And for people who are like, I don't want to understand all this stuff, Keras is awesome because you don't have to understand it. You can kind of just build your model, see if it works. It does a lot of stuff for you. Yeah. So Keras is built on top of Theano. So like all this stuff that we just did, we'd like to combine it into one thing. So we don't want to have to make our weights here. We don't have to want to initialize our layers. We kind of just want to say, give us a two-layer neural network and train it. And we don't want to have to we don't have to put these like cost functions in, make the update rules, stuff like that. We just want it to be done for us. And Keras does that. So yeah, so here we have the input data again, x and y. And now we start building our model. So this is the same code that we did before. We define an input variable, input layer. We define a dense layer that goes on top of it. So a dense just means that's a matrix multiply and bias and nonlinear function. Like this part would be a dense layer. And we can define the activation function. So I put relu here, but we could change it to the different activation functions that you know of, or look up sigmoid. Yeah, tan-h is another popular one. So yeah, so we can just plug our relu function in, and we want to say 5 hidden neurons. So we have an two input dimensions. So we pass it vectors with dimensions 2, and we have 5 hidden neurons. So it multiplies it by a 2x5 matrix and adds a bias vector of size 5. And then we have another dense layer that multiplies that output, the 5-dimensional vector, the hidden vector, by a 5x1 matrix to give us an output of 1 dimension. There we go. That's how we build that model. Super easy. Don't have to do all the stuff that we did before. And we can define our inputs and outputs here. We build a model that takes the input layer and gives as output the output layer. And we can compile it so that it optimizes using, we can change the optimizer if we want, but the optimizer subgradient descent just refers to this process here. So again, if you don't want to understand it, you don't have to understand it. But basically, different optimizers do different things, and we can experiment with those. And the loss function is the cost function that we used here. So like, how do we define outputs close to inputs? this is a good one. This is a good way. So mean squared error is a good way to define outputs close to inputs. You might also say we want our cost function to just be like y minus output, because if y is close to output, then y minus output will be 0, or close to 0. There's different ways to define that. But again, if you don't want to worry about that, don't have to. And lastly, we can go ahead and train it. Yeah, so the error went down again. So it works. So did this make, go ahead. Yes, that is true. I mean, it's like a stochastic process, right? So you never really know like this is gonna work or not for your presentation. Yeah, but it went down is the gist, and like, I mean, a lot of this is like twiddling around to see what'll make it go down the most, what'll make it go down the least. I tell my girlfriend just like I play around with numbers all day to make them smaller, because that's the easiest way to explain it. You're trying to make the loss get smaller, so yeah. Yeah, so did that make a bit more sense? Or is everyone lost still? Great, because it'll get a bit harder from here. So Keras is still very much under active development, because life is still under very active development. And we want to, do cool things, and sometimes Keras might not support those things. So a lot of what I was going to talk about in this talk was how to make Keras do those things. Because you can, and that's what makes it an awesome framework for developing stuff. So, first, raise your hand again if you were interested in like natural language processing or language modeling. Okay. So how many people have heard of word embeddings, or word2vec? Word2vec, or glove is the other one, I guess. Similar concepts. They all refer to the same thing, and that thing is how can we put if we have a section of words, maybe like the Wikipedia corpus or something, how can we learn a model that embeds each word into a vector space, and that vector space tells us something interesting? So what I mean by interesting is it figures out semantic relationships. So for example, kind of the canonical example is like you might have like the vector for king minus the vector for man plus the vector for woman gives you the vector for queen, right? So that's sort of that's the one that they used in the paper describing word2vec, I think. And that's pretty cool. Like that's demonstrates a really high level of understanding for a model that's kind of untrained, and that's so you can do a lot of stuff with that. So let's talk about how to do that, or like what that means. And to do that, we're going to train a really easy task, or like a trial task. So here, okay, so word embeddings are used as an alternative to like an alternative way to encode your words in a vector space. You might define your vector space as like 100 dimensions, and within that vector space, that's where all your semantics are related. So one dimension might be like, animal versus human or something. Each dimension kind of tells you something about the word, and that's really not only interesting, like from a language view, but also saves computer space, because if you only have 100 dimensions versus like 2,000 words, 220,000 words, that's very efficient. So let's look at the alternative first. The alternative would just be to say, for each word, let's make if our vocabulary is like 10 words, we'll say, we'll make each word represented by a 10-dimensional vector, where each dimension in the vector represents whether or not that word is the word, right? So the first dimension might be the second dimension might be brown fox jumped over the lazy dog. Each dimension, you either have a 1 or a 0, and there's only one per vector, and that's called one-hot encoding. So one hot dimension for each word. Yeah, so there we go. Does everyone understand kind of where this comes from? Everyone following? So the one-hot encoded vectors, each vector is a row, and there's one per row, and the 1 refers to the word it is. Right. So so what's the problem with this? Does everyone have an idea? Too many vectors? What? A lot of zeros, yeah. No way to associate overlapping semantics, right? Yeah, those are exactly the problems. And like, how many unique words do you think Wikipedia has? Anyone want to guess? Yeah, start with English language. 50,000, maybe a bit more. Actually, I should Google it. How many unique words does Wikipedia have? I was gonna guess like 200,000, but does anyone see it? Here? Yeah, that's total words. I didn't see number of unique words. A million. Okay, we'll just go with a million. That's a lot of words. And if you had to represent each word as like a million-dimensional vector, 32-bit integer, how many bytes is that? It's a lot of bytes, even for the Cookie Monster. Sorry. I was going to take this seriously. Okay, so better approach is word embeddings, which is why I have this. And as we were saying, we'd like each vector here, instead of being a one and a bunch of zeros, to be like have some information about the semantics, as you're saying, like, and also be smaller. So we're going to train a kind of toy example to do that type of problem. So this, I have a lot of friends, well, 4 friends, who like have certain colors associated with them, red or blue, or red or green. And I was like, oh gosh, I wish I had a way to determine if my friend is red or green from the sentences that I wrote about them. And so yeah, let's go ahead and do that. So we'd like to figure out how to make word embeddings that can tell us whether my friend Sam is red or green. So we can put together some training data. For each sentence, we'll say 0 if red, 1 if green. So Hannah not red, she's green, so it's a 1. Hannah is green, it's 1, she's green. Bob not red, also green. So we've got these sentences. And next, we want to split them into the individual words, because those are what we're trying to embed. And we can make convert from word to index and index to word. So what I mean by index is when you build this big matrix, each row is going to be related to a certain word. So the index of a word corresponds to that row in the matrix. I want to be able to convert between rows and indexes, or words and indexes, so that we can use this and train it. So for example, so this is all the sentences converted. So Sarah is represented as 0th index, Sam is 1, Hannah's 2 is 3. So this sentence is the embedded version of Sam. I guess Sam is red, 137, same as red. So that's how we represent a sentence as a list of indices. And now we can go ahead and try to learn some embedding. So now this kind of tells us a bit about our corpus. So we've got 3 words per sentence, 8 total words in our vocabulary, so 8 possible indices, 0 through 7, and we want to embed it in a 2-dimensional space. So why 2-dimensional, do you think? What? Yes, so we can plot it. That's exactly why. So if we were doing something like Wikipedia, you know, how many dimensions would be a good idea for that task? A lot? How many is a lot? Is it 500,000? Oh, 500 or 1,000 for 1,000,000 words. Yeah. So I guess anyone else want to like guess, or I mean, if you're interested in LLP, what do you think? Well, okay. The answer I was looking for was it depends on the task. So yeah, so we can't actually know. But 500 to 1,000 is probably a good number for the task, like kind of whatever task we're trying to do. And I guess it depends on the things that we talked about, right? Like, are you constrained for space? In which case, lower dimensions is better. Are you trying to, like, is this word embedding your total model? Like, is it really important to have really good word embeddings? Or do you not have much data, so you need to like make a smaller dimension to avoid like overfitting the data or something? Yeah. Anyway, so we're going to do 2 because we can plot it easily. And this is how we do that. So we'll say, this is Keras again, back to Keras. We have an input, which is our sentence, and that has shape sentence max lane. Each sentence is three words, so we want to have our input shape be a 3-dimensional list, or like 3-word list of indices. Encoded as integers because they're talking about the indices, right? So like it's going to look up in our matrix which row corresponds to which word. And then we have our embedding layer, and the embedding layer is basically like the matrix of all the words, all the vectors that represent each word. And then we have on top of that an average pooling layer. So don't worry about this. Basically what we're going to try to do is we're going to try to train the model to make the red people go to, sounds sort of racist now that I think about it, but like the red people go to 1 or 0, sorry, and then the green people go to 1. So yeah, so that's what we want our dimension or our embeddings to represent, is whether or not the person is red or green. Yeah, and so everyone following along here? Just want to kind of gauge where everyone is on this. So now that we've got this model set up, we'll go ahead and predict it and then print the vectors that it learns. So here we go. Predict green. So we built our model that takes the input sentence as input and outputs the color prediction. And we compiled it using our subgradient descent optimizer. And instead of what was the loss we used before? What? Mean squared error, yeah. So instead of that, we were going to use a different kind of loss called binary cross entropy. Binary cross entropy just means it's either 0 or 1. So if it's a binary classification problem, binary cross entropy is a good one to keep in the old noggin. And then we're going to fit it. So we're going to run it for 500 or 5,000 epochs. Given our sentence data, our sentences and our desired color predictions, We're just going to run that for 5,000 steps. And then we can get the embeddings as the weights of this embedding layer, or the matrix associated with this embedding layer. And once we have that, we can, for each person, we can present, or for each word, we can print the vector that is that word embedded, right? And yeah, so that's really cool, right? Like, does that make sense to everyone? No. They are all close to 0. Yeah, the loss went down. I think that's kind of more has to do with the way that we initialize the weights rather than anything. It wasn't training to be 0, but yeah. So let's go ahead and plot those, as was the purpose for making this, and it didn't work. So we're gonna have to go to the plots that I made beforehand, because those actually worked. Yeah, so when we embed our vectors, Sam and Sarah, so Sam and Sarah were red, and they're in their own corner in the vector space, and Hannah and Bob are green, they're in their own corner in the vector space, and all the other words are kind of there. So what this model is saying is we can embed these vectors into a vector space so that the location can kind of tell whether or not that word is associated with being red or green. So based on these sentences, like I included like is, not, and red. Like not, like red can either be associated with red or green, but Hannah can only be associated with red or with green, just because of the way they are with the sentences. So you can't get any information out of the is and colors. It's just the people's names that you want to worry about, and that's what the model figures out. So that's word embeddings. Does anyone have any questions on what we did there?
Is there any meaning for magnitude of 1 is 2
What? So yeah, is there any meaning to the magnitude? What do people think? Yes. Why? What? What? Yeah, what is the meaning? I don't know. How often it's coming? Mm-hmm. So the exact model that we're training is basically, I'll go and talk about it again. The model itself learns to make the embeddings such that the average over the embeddings is close to 0 if it's associated with green, close to 1 if it's associated with red, I think. Yeah. So if we have a sentence, yeah, so this is close to -1, I guess. And then this is a little bit, that like offsets it a little bit. So together, if you sum like Sam plus is red, it would be close to 0. And if you sum Hannah plus is green, it'd be close to 1 maybe. I think that's the idea. Good question. So any other questions about how we do this? So this is very important for a lot of natural language processing tasks, especially when we build a deep learning model, because as we were saying with the dimensionality problem, if we feed a million dimensional vector into a deep learning model, you're gonna have a bad time, because it's really hard to not, you want to start with some idea of what the words mean in order to build a model that processes them. Also, the speed thing is important. You don't want to do a lot of multiplication by 0. Yeah. So let's get into the heart of it. Kind of change gears and focus on another topic called recurrent neural networks. So who here has heard that term before? Maybe 50%. Does anyone want to take a shot at what they are? Neural networks for time series, yeah. How do they model time series? Right, connect the hidden states between two steps. So we had our model before that was, we had a input and then there was a hidden layer and an output. So if we want to provide multiple multiple inputs, like a time series of inputs, and we want those to be related to each other, basically what we're going to do is we're going to have a hidden state that kind of changes each time we provide an input and gives an output. But it keeps information about the previous input and all the history, so it can learn these sort of time dependencies. Does anyone think they might know why that's important for a language modeling task, or why that might be helpful? So you can understand the whole sentence and sequence of words. The order of words matters as opposed to bag of words. So what might be an example of that? What if? What? It is. That's a good example. It is okay not to come. Is not okay to come. Or grandma rode a train versus a train rode grandma. Also, important instance of like the order of words mattering a lot in the meaning. So a lot of conventional natural language processing algorithms aren't very good at capturing these time series relationships. So for the people here who are interested in NLP, what kind of machine learning algorithms do you use typically? Latent Dirichlet analysis. So I think that actually is supposed to capture some semantics, right? Mm-hmm. Okay, yeah, I can see that. Yeah, it's a bag of words model. So a bag of words model basically means like we represent a sentence as the words that are in the sentence. So like that's what that would confuse the sentences we were talking about earlier, because it doesn't know the relationships between words. It works pretty well for a lot of stuff, but maybe there's some stuff, and actually like a lot of this stuff is pretty new, so people are kind of starting to see new things that it might be useful for. What I'm going to talk about later, if there's enough time, is using that for answering questions. So like it's kind of hard to model. There's some theory on the order of words in a question matters in terms of the answer we want to provide. That's kind of intuitive to a lot of people, but before we were able to do these sort of huge data sets with these complex models, that wasn't very popular. Like people were like, oh, we can just say like, what is the answer to 6 times 7? We can just represent that as the words, what answer 6 times 7. So this is a recurrent neural network. This is the diagram of the 2-layer neural network that we did in Theano, a 1-to-1 mapping, and we're going to want to expand that to a recurrent version, which we have one input maybe, and then we want to get a time series of outputs. Does anyone have an example of what that might be. Like when would we want to model something that way? Sorry, what? The one-to-many model. So given one input, have many outputs, what kind of models might that be useful for?
Sentence that have multiple meaning. Doing Google search.
Okay. One sentence might have multiple meanings. Yeah, that would be really cool. Like, that would be cool if you could like give it a genre and it would like give us a sample sequence of that genre's music, like a time series of music. Yeah, I wonder if anyone's done that. That's pretty neat. So you can do all sorts of different kind of recurrent neural network architectures. Many to one might just be given a sentence, say if that sentence is happy or sad. It's a sentiment analysis, I think. And then many to many models usually is for maybe mapping one sentence to another sentence, or like a sentence to a like song or something like that. You know, time series to time series. So now that we've got that all easy squeezy, I was gonna go ahead and devote a little bit more time to actually understanding these and building these yourselves. So did everyone get these installed? Raise your hand if you didn't get it installed. Oh, it's okay. Okay, so yeah, so okay. So everyone have like a Python IDE that they want to work in? I'll go ahead and open up. So I'm in the directory that I was just working in, or the directory where I installed the notebooks. Go ahead and activate the virtual environment. This is really hard to see too, right? Oh. Is that better? Probably not. Okay. Can everyone see now? Okay. Yeah. So let's go ahead and activate our virtual environment. And we'll make a new file called rnn.py. Okay. So because I'm using Python too, I always like to do the from future import print function. And let's import Theano. And from Theano, import tensor as T, capital T. This is kind of just a good convention to do. And let's import NumPy as NP, also conventional. And let's seed our random number generator with the answer to the life, the universe, and everything. And make another random number generator for using elsewhere. Yeah, so in Theano, to do these matrix multiplications that are kind of at the heart of our neural network models, we want to be able to do those on a GPU because GPUs are really fast and really good at matrix multiplication. So Theano and also TensorFlow and also Keras provide an easy way to do that by basically abstracting it. So because I'm not on a GPU, the data type here, float X, is float 64s, but depending on your GPU, it might be 32-bit floats is pretty standard. So yeah. So once we have our model, we want it's very easy to just put it on a computer with a GPU and away it'll go much faster than it would work on my laptop, for example. Okay, and like we did before, we want to make helper functions to create, to initialize our vectors or our matrices, our weight matrices that represent each layer. And so when we say get weights, this means we want to initialize a n in by n out matrix. So if we have an input vector that has dimensions n in, and we multiply it by a weight matrix like this, then the output vector would be what? It'd be an out, right? So that's the heart of the neural network, and it's pretty important to understand kind of how we formulate this. So the way that we initialize these weights is we want them to be random. We want random initialization. So that helps us ensure that when we learn this model, it's not gonna, all the weights are gonna learn kind of unique things about the model. They're not gonna learn the same values. So if they're all the same weights to start off with, then they probably will learn the same values. It's not going to be very interesting. So we want to add some randomness in there. And the way we add the randomness is kind of this strange formula. Basically, we want random numbers between this value and the negative of this value. So let's create a NumPy array which is doing that. Okay, that's our W value. And then now that we have a NumPy array, we want to be able to put it on Theano, and Theano will handle putting it on a GPU for us and being able to do calculate derivatives that NumPy can't do that. And Theano will also do a lot of optimizations to help our model run faster. Yeah, so let's turn it into a Theano shared variable. Oops. We're just going to name it W underscore number of input dimensions underscore number of output dimensions. Borrow is true. So borrow is true means is Theano is going to just use the memory allocated by NumPy to store the matrix. So it's not going to copy the matrix to new memory. And strict is false is just some extra stuff. Basically, strict is false means we can multiply suppose we have a matrix of input vectors, we can multiply that by our weight matrix, or we can multiply vectors by our weight matrix. So yeah, and return the Theano shared variable. And we'll do the same thing for the bias function. And unlike with weights, it's usually a good idea to just set your initial biases all to 0. I think there's a mathematical explanation for that, but I don't know it. So I think I can just ignore that. And again, we start off with a NumPy array, and then we convert it to a Theano shared variable. borrow is true again, and strict is false again, and return B. Okay. So now we're going to learn our optimizer. So let's try making this subgradient descent optimizer we were using before, SGD. So SGD would maybe take cost and params. So parameters those are the parameters that we're learning. In other words, the weights of the matrix and a learning rate. And the equation, which we had over here, is updates equals p minus learning rate times t dot grad cost with respect to p for p in params. And we can return updates. So our subgradient descent optimizer, it's just going to calculate how much do we change the weights for each time we give it data, how much should we change the weights of the model so that we learn something useful. Yeah. So we'll come back to this later because subgradient descent is just, it's one way to learn to change these weights, but there's other smarter ways depending on your model that kind of can do more mathy stuff. And if we want to make a really good model, we need to take those into account. Okay, so let's also generate a generic function for testing our model. So if we have a model, we have like n input dimensions, n output dimensions. Our input Theano variable, which is just a placeholder for passing data, and our output of the model, and then the parameters of the model. We want to make a function that'll just be able to test that model on some dummy data. So okay, so our testing function will basically, it'll calculate the updates. Oh, I should change this to our subgradient descent optimizer. It'll calculate the updates, and it'll create some. This is just some random data, x datas and y datas, so just random vectors of data for us to use, and it'll train the model to map the x data to the y data. In other words, it'll learn. So yeah, and this is just down here some evaluation stuff for doing that. Now let's get into building a recurrent neural network. And so this is how we specify the network is going to be with we have n input. We set the number of input dimensions. We set the number of hidden dimensions. In other words, the size of this matrix. So each arrow here represents a matrix. So this arrow would be n in to n hidden. These arrows would be n hidden to n hidden, and these arrows would be n hidden to n out. Okay. And yeah, so let's see what we need to do for this. First, we want to have a variable representing our input. Oh, before I forget. Oh, never mind. So we have a variable representing our input data. So this variable is just like a placeholder. when we said like Theano does a lot of optimizations, it needs to know what it's going to be optimizing on. So we give it a placeholder that stores the like the data we hope to pass it. In this case, we're going to pass it a matrix. That's going to be like a matrix where each row represents an input vector, I think. Okay, so the next part of the model is, as we were saying before, we have 3 different weights for our vanilla network. This weight, everyone see? We have this weight, the input weight. We have this weight, the hidden weight, and we have this weight, the output weight. Those are 3 sets of matrices that we need to represent. So let's go ahead and use our getWeights function to represent those. So for the WIN is the input to hidden connections. So that will be, if we have a vector with n in dimensions, we multiply it and we get a vector with n hidden dimensions. And those are the hidden states of our network. This vector will be, or this matrix will be the hidden to hidden connections. So this is what's going to help model the time series data as these hidden to hidden connections. So on each time step, we take the previous hidden state and we multiply, like the vector representing the hidden state that we got from the last input. We multiply it by this hidden connection matrix, and we get a new vector representing the new hidden state. So, and that's important because it'll help us with these time series data. And finally, we're going to have an output matrix that's going to be it's going to be from the hidden state that we have. So we calculate the hidden state, and then we're going to multiply it by a matrix to get a number of output dimensions. Yeah. And then we also need biases for each of those. So, we don't need a bias for the, so with the input state and the hidden state, what we're going to do is we're going to multiply the input by the input matrix, and we're going to multiply the hidden state previously by the hidden matrix, and then we're going to add those 2 together, and we're going to want to bias that sum. So we'll just call that bias be hidden. And another bias function, or the other bias we're going to have is the output bias. So, for the output of the matrix, or the output of the network. And we're also going to have a hidden state to start the network. So if we need to take the previous hidden state at every time step, what do we do at the first time step? We're just going to have the hidden state start at 0, and then it'll do its operations, assuming 0 is the previous hidden state. So that's H0. Okay, and all the parameters of the model are our weights and our biases. So WIN, W hidden, W out, and B hidden, B out. And also we're going to want to change the H0 of the model. So we want to learn a good starting point for each, for our network, like a good starting hidden state. So we're going to want that to be part of what we learn. And now let's define the recurrence relationship. So this is really the heart of the network, and this was really tricky for me when I was picking these up. This is going to be where we actually define what to do on each time step. So given an input x of t and a previous hidden state h of t minus 1, let's say the new hidden state, we're going to apply our nonlinear tan h activation function to the dot product of the input vector with our input connections, our input matrix, plus the dot product of our hidden state, our previous hidden state, dotted with our input, or our hidden to hidden connections, and we're going to add our hidden biases. Yeah, so we're going to add the bias on our hidden. So this is how we get a new input state, or new hidden state on each time step. So does anyone have questions about this? No. Okay, so now that we have our function to determine the new hidden state, let's get the output from that hidden state. So basically, given the hidden state, we just want to apply a nonlinear function to the dot product of the hidden state with our hidden to output matrix, right? And our nonlinear function in this case will be a sigmoid function. So h of t is our hidden, and our w out is our hidden to output connections, and we're going to add our output bias. And lastly, so now that this function step defines what we do at each time step. So we want a way to apply that function to every step in our input. And to do that, we use a function called Theano.scan. Theano.scan returns kind of some weird stuff, but we want to basically all we want is the output of doing this operation on every time step. So our function that we run on every time step is called step. The sequences that we input are x is the placeholder variable, and outputs info, don't worry about this, some boilerplate, and we run it. So n steps is just the number of steps to run the function on. So in this case, x.shape 0, the first dimension of x, will represent the number of time steps, and the second dimension will represent for each time step, that's the input vector. So we have x is a matrix. The second one will be the first dimension represents the time, and the second dimension represents the data. And now let's just run our test function on the test function we wrote earlier. You can just run that on our network, and cool. So yeah, so then we'll just test the vanilla RNN. And say vanilla because this is like the introductory architecture. So yeah, so Python rnn.py. Oops, there's going to be a lot of bugs because I was using Vim. Oops. I'm blaming you guys for this because she caught these while I was writing it. Where is that? Oops. Oh. should be called tests. Oops. Non-keyword arg. Oh. So right now, a lot of what's going on is Theano is making these optimizations and storing stuff in the right place in memory. So we start off with calculating the error. The starting error is 15.9748, and then on each time step, so after 200 iterations, the at learning rate 0.1, so change the learning rate on each, like progressively, but the error goes down to 10 and then 2 and then kind of stops around there. So so the function or the model works pretty well. The error goes down, the numbers go down, which is pretty cool. Yeah, so does anyone have like kind of talk about RNNs and why there's problems with them? Does anyone kind of have an idea of why this model might not work so great? So what if the sequence is really long? Let's take a look at our equations again and get the idea of our update rule is for each parameter, we're going to change that parameter to minimize this cost. So we need to get the gradient of the cost with respect to that parameter in order to know how to change that parameter, right? So if we have a really long sequence, we have to get from this input, this weight matrix here, to this output matrix, or this output that we have we can calculate the cost function up here, and then we need to figure out how does this cost change with respect to this this weight matrix over here, right? And if our sequence is really long, what are we doing here? We're doing a bunch of matrix multiplications followed by a nonlinear function. So if we do that over and over again, the amount that this matrix actually affects the cost here is gonna get smaller and smaller, right? Because if we for each step apply a nonlinear squashing function, it's going to get diluted. The gradient's going to get diluted, so it's going to be harder to say how much do we change this parameter in order to get a value of the output that we want. So that's the problem with recurrent neural networks in their basic form, and that's why I called this the vanilla RNN, because we can do cooler stuff to be able to get this to work. Okay, and before going into what that cooler stuff is, let's take a look at the other cost function. So right now we have our subgradient descent optimizer that takes cost and the parameters that we want to change to decrease that cost, and a learning rate, which basically how much we want to change the parameters on each step. So instead of using, what this is saying is just change the parameter in the direction that minimizes the cost with respect to that parameter, and change it a little bit by the learning rate. So there's better ways to do this, and one of them is called RMS prop. There's a whole list of different things that we can use for these, so RMS prop is one of them, and RMS prop probably don't really need to understand it too deeply, but basically what it's saying is like we want to make sure the gradients kind of make sense for what they should be. So for each weight matrix, we want to kind of stabilize it, so we're not changing it a ton, but we're not changing it too little, and that helps us helps the weights learn faster. So yeah, so that's a way to improve on the basic subgradient descent idea. And so let's change our optimizer to RMS prop. And you can just rerun it again, see if that makes a difference. Again, like the numbers will, so training neural networks is difficult because of this really nonlinear space that we're trying to learn. It's not easy to train it. So sometimes you might get like this, like ideally RMS prop works better, but in this case the cost didn't go down as much as just using the subgradient descent optimizer. So we can, like, if you're building a neural network in a production scenario, it's a good idea to want to try out a bunch of these different optimizers to see what works the best for your data, and try it quickly without having to write all these functions. Anyway, so I was saying, so this is the problem I was talking about earlier. Officially, it's called vanishing gradients. So that's just the problem of we can't determine how much this parameter affects our cost here as easily, because the gradient gets smaller and smaller as we go backwards in time, and that's illustrated here. So this is the RNN on the right, and the noise kind of represents how big the gradients are. So I guess this is like 128 time steps, but after 20 time steps, the gradients basically disappear. In other words, at the start of the sequence, that changing the parameters at the start of the sequence doesn't affect how much the network, or how much the cost function changes at the end of the sequence. So in terms of modeling stuff, does anyone see why this would be a problem? Suppose you have a really long sentence. What kind of problems would you run into with this? Right, you're effectively not paying attention to the beginning of the sentence, and that might be important. So there's better ways to do this. So the network on the right is a modification of this recurrent neural network architecture that will basically pay attention to the stuff at the beginning. And it's called long short-term memory. It's very hot right now. Everyone's doing it. So you should too. And these are like the descriptions of the two architectures in comparison. So this is what we had in our functions, right? We have a hidden state here that gets outputted. That's our hidden state. And we take the hidden state from the previous step, we feed it in, we add it to the new input state, we add those together and apply our nonlinear function, and then that gets our new hidden state, and we pass that along to the next time step, right? So this is basically what the equations up here were doing. And our LSTM network is going to help solve that, basically by just being more complicated. We just add a bunch of stuff, and basically what these are adding is they're gates, and what that's going to do is going to say, let's store the information from earlier in the sequence and then let it drip back into the sequence later on. Like in memory, you might write to memory and then read from memory in a computer science metaphor sort of way. And we're going to write to our storage unit, and then we're going to read from that storage unit. And that'll help make sure that the gradient of the cost function with respect to stuff early in the network is still there, right? Because if we can store the information from the earlier in the sequence and just loop it around to the end of the sequence and have that affect the cost, it's gonna have a much more direct impact. So without going too much more into the math, the idea is that you can model long-term sequences with by paying attention to the stuff in the start, and these are the equations for doing that. So a bit more complicated than the RNN equations, obviously, but I think if you wanted to learn a bit more about this and kind of plunk away at this, these might start to make a bit more sense. Basically, we have a forget gate and an output gate, and the forget gate just tells you so we have this candidate state that we're kind of storing from the beginning, and the forget gate says how much should we swap out the candidate state, there'd be stuff from the beginning with stuff from now. As we go through the time series, how much do we want to update this state? So we can turn off the forget gate, and then it's just going to keep all this stuff from the beginning, and that's how we avoid this vanishing gradients problem. Yeah, so obviously a lot longer than the other one. But let's go ahead and comment that out. Set no pay or set paste. Oops. Wait a minute. Yeah, so, but basically it's the same formulas and same format. So we have our list of parameters for the net. So this is just the weights and biases of the network. We have our different, all these different weight matrices and bias vectors, and we just add them to this list of parameters that we're going to store, and we're going to calculate how much the gradient changes, the gradient of the cost function with respect to each of the parameters, and we're going to update the parameters in such a way that the cost function goes down. In other words, our predictions improve in accuracy. And this is the step function. So at each time step, we do all this math stuff. Yeah. Yeah. So let's just try that out. So ideally, what would happen if this works correctly? What do you think would happen? Using the LSTM instead of an RNN, what's going to happen? Actually, wait, I'm going to turn it off for now. Decreases the error, yeah. Why would it decrease the error? Yeah, exactly. Oops. I need to plug in. So again, right now it's basically setting up our weights and putting them into memory in the right place and making optimizations to help it run faster. And so after LSTMs, there's another one called GRUs, which is another way of solving this gradient issue. Not super important to understand how these work, but yeah, good reference. And here's a testing function for trying that out. Here we go. So it worked like it was supposed to. So remember our error was like 2-ish after the first training step. Now it's gone basically to 0. So the LSTM has done a much better job at modeling the time sequence. So yeah, so last part is why do we do all this if the talk was going to be about Keras? Basically, it's to illustrate like that's a lot of math, and we don't want to have to do that every time. So this code does all of that in Keras in like way less math. So we have our input, we generate some input data the same way, and then we define our model. You know, we have our input sequence going to be it's going to be input length and input dem. So the sequence length is like the number of time steps, and the input dimensions is it's the length of each vector. So each time step has a vector. That's the size of that vector. And then we can literally, instead of having to do all that math, we can just say simple RNN, specify the number of output dimensions, LSTM, specify the number of output dimensions, GRU, specify the number of output dimensions, and significantly easier. You know, just one line of code, and we can test it out. So the errors are kind of weird here, but they learn. So that's the moral of that story. And so finally, let's see how to modify Keras. So like Keras is not not restrictive. Like you don't just have to, you know, if you have this type of network, LSTM network, how do we build on top of it? And Keras got a lot of good support for that. And so to talk about doing that, I'm going to talk about a popular application right now, which is adding attention, so making your network pay attention to stuff. And this was a really cool paper. I don't know if anyone can see this. Oops. Can anyone see that? Or probably can't read this stuff. If you have it on your laptop, then probably it's easier to see. But basically, if you feed it in an image and you train a network to write a sentence describing that image, which is really cool because, you know, say you're like making a user interface for helping blind people, like you could, you know, use some text-to-speech thing that would tell the blind person what the image is about, along with a host of other ideas. And this is a bit of a complicated architecture to try to build in Keras because it's new and you know, Keras only gets developed so fast. But the way the architecture works is we have this sequence or this LSTM that basically goes through, you know, traverses the image kind of in this way, and then it pays attention to certain parts of the image. It's trained to pay attention to certain parts of the image. So the highlighted part, I don't know if you can tell, but this is a picture of a woman playing a frisbee with her I guess kid, and the network basically learns to light up for the frisbee. So it's paying attention to the frisbee, so that when it writes a sentence about that image, it can highlight, like it knows it's about a frisbee. Yeah, so this is a cool task, and attention is one of those things that's like very hot right now with like startups and stuff, I guess. But something that, you know, not easy to do in Keras, but we can do it, and let's see how we do that. And to do that, we're gonna generate some sentences, some sentences to model. Basic sentences like the cat in the hat is in the barn. The cat in the hat is in the house. And then we're gonna ask questions. So is it wearing the hat? We're gonna say the sentences that are true for this are 0, the cat in the hat, 1, the cat in the hat, 4, the dog in the hat, and 5, the dog in the hat. So these are all the true answers to those questions. And we want to train a network to say, like, given a question and an answer, is that answer true to the question, right? And does anyone have any ideas of, like, you know, a real world application that might be kind of like this problem? Google? Yeah, probably. Yeah, type in a question. Jeopardy? What? Online learning? What do you mean? Oh, yeah, like automatic assessing. That's a cool one. Yeah, Siri. Yeah, Siri is a good one. Yeah, so all sorts of applications for answering this type of question. There we go. Text to speech. Yeah, so this is the question, and these are the answers that fit with that question. So, is it wearing his shoes? Cat in the hat and the shoes, or the cat in the shoes, dog in the shoes. Yeah, so this is our training data. And again, we're going to want to tokenize it, and we're going to make a list of vocabulary. And we want to use this vocabulary to turn our sentences into indices, right? Like from our embedding. This is our vocabulary, our dictionary from word to index. So for example, wearing is going to be row 1 in our embedding matrix. Next, we just turn those into NumPy arrays. So we encode, and we have a function for encoding sentences as NumPy arrays. And we're going to want to apply that to all our data. And we get something like this. So 48 questions in our training set. Not 48, but like 48 question answer pairs. This is our input questions, our input sentences, and then y is whether or not that sentence matches with the question. And now we're going to get into the hairy part of adding attention to Keras. So making Keras, our LSTMs, pay attention to the stuff that we want them to pay attention to. And this is pretty cool. So our attention mechanism will basically say, it's this part. It's given we have this vector that we want to pay attention to. So this could be, we encode the question, and then we want the LSTM that's going over the answer to pay attention to the vector representing the question, or use the vector representing the question to decide what words it's going to pay attention to in the sentence. And basically, so each time step we get a hidden state. We're just going to apply this way to like combine these together and learn to pay attention to certain stuff. But what it ends up doing is, for each word, it increases or decreases the activation on that word, and that's going to be important for determining which words are, like, the amount that the attention is active basically tells us how important is that word, or that's what we want it to do. And this is kind of a diagram of, so this is all the LSTM stuff, but this part right here is the attention mechanism. So we provide an attention vector to our LSTM, and that modulates the hidden state over time. And let's do that. So this is all the code for that. I mean, it's kind of a lot, but if you look at the Keras code base, it's not very much in comparison. But it basically wraps around the LSTM layer and modulates it, it trains it to use attention, pay attention to stuff. And then we generate our model. So our model is going to be input sequences, 2 input sequences, the question and sentence. We have our embeddings layer again, so we embed each word in the question and sentence into a 10-dimensional space. Because we don't have many words, we don't need that big of embedding vectors. And we apply the question embedded and sentence embedded. We're going to apply the embeddings to each of the question and sentence. And then we're going to do something called, so then we're going to apply our LSTM encoder. The LSTM will basically read in the sentence and output a vector. It's like it's this type of model here. It'll read in the sentence and output a single vector, which is kind of the sentence encoded. So we have our LSTM that we're going to train on the encoder, and we have our attention mechanism that we're going to wrap around the LSTM that is going to pay attention to the question encoding. So this part. And we're going to apply that LSTM to the sentence. So the sentence encoding is going to depend on how we encode the question. And for our learning rule, what we're going to do is we're going to take the cosine similarity between the encodings of the question and the sentence. So does everyone kind of know what cosine similarity is between 2 vectors? It's like the angle between them. So if the question and sentence match each other, we want them to be like a small angle. And if they don't match each other, we want it to be a big angle. And this is just some math saying that idea. And we're going to have our model. Again, we're going to use a RMS prop, the optimizer that we had before. RMS prop in particular works well for LSTMs and time series data. And our loss is going to be mean squared error. We're going to want to just set a target, and we're going to, our loss is just mean squared error between the target and the prediction. So this is the shape of our model. None means that's like the batch. So each batch could be like, you had a batch of 15 samples or 100 samples. None is just a placeholder for whatever number of samples you want. 10 is the length of the sentence. So each input is going to be a matrix of where each row is a sentence, and then there's like the number of rows is the number of batches in that training set. And we're going to output a shape that's just like for each row we want to say does it match, does it not match. So it's just going to be one choice. Yeah, so I went ahead and trained that, and it trained pretty well. The numbers went down. So one thing about Keras is it's got all the boilerplate for being able to train your models without having to write these complicated training functions. You just say model.fit input data, output data, batch size, number of epochs to fit it for, and then some random other stuff. Callback in this case, once the error is below a certain threshold, stop training. And let's plot the error, or the loss function. So it goes down almost to 0, which is what we want. Numbers going down. And yeah, so our model we learn to model this data pretty well. And the interesting part is, let's figure out what it paid attention to. So that's what these are. So given a sentence or a question, is it wearing the shoes? And we have an answer, the cat in the hat is in the barn. So is that wearing the shoes? No, it's wearing the hat. And actually what happened is it decides not to pay attention to the word hat. Like the attention on hat is very small. Whereas, so that's not a match. So is it wearing the shoes, where the answer is the cat in the shoes is in the barn? The attention on shoes is very high. Well, so everything else kind of stays the same, but the difference is it pays attention to hat in this case, or it doesn't pay attention to hat, does pay attention to shoes in this case. And yeah, if you go on to GitHub, you can kind of figure out patterns from what this is doing. So yeah, that was basically a very, very fast introduction to all of deep learning up to about a year ago. I think this is sort of outdated now, but I don't know. There's the paper that I based this off of was like published a year ago, so very, very fast, but hopefully everyone got something out of it. Any question? Oh, if you wanna actually like look up, I wrote a big blog post about all this stuff, which you can see. I think I linked to it from the presentation, but it's kind of got all this stuff in greater detail. There's two papers actually, this one and this one. What? Oh, sure. The authors were all from IBM actually, so kind of coincidence. This paper, so the first paper was applying deep learning to answer selection, a study in open task. So this is kind of a classic NLP question, like given a question and an answer, choose, and a set of answers, choose the best answer. It's like exactly what Google does. Has this list of documents and has a query and tries to figure out which documents best match the query. And this paper did that using, I don't know if you can, this paper did that using convolutional neural networks, which are just another type of neural network that are very popular. And this other paper did that using LSTMs with the attentional component built into them. So given a question, if you have this attentional component added on, it makes it easier to separate the good answers from the bad answers. Yeah, so that's pretty much it. I was only planning on talking for like 90 minutes, but kind of because of flight issues got switched around, so.
Any more questions for the speaker?
I think Bowen Joe is the guy who did both of them, the PI for both. These are both on our archive, but I guess ICLR and. Do I have time left? Or I could show you how to put it on. So like running these models on my laptop doesn't work very well because it's not very fast, but you can put them on Amazon Web Services or Google Compute Engine. Those are both good options for running complicated models in the cloud. I happened to have one of my professors had credit for Google Compute Engine, so Oops. Ooh. I changed my phone number recently, so this probably doesn't work actually. Yeah, I'm pretty sure it doesn't work. So I'm pretty sure I'm locked out of my account. Oh well. Hmm? Oh yeah, but I changed my phone number, so I think it, new phone and all, doesn't send it to the right phone. Well, I'll tell you what would happen. Basically, you can, if you want to check out the other repo that actually has got like a lot of this stuff implemented for a real life task. It's this repository right here, code Kansas / Keras - language - modeling, and it's got kind of I've got instructions on here for how to get deployed on a Google Cloud Platform instance. There's like an install script. And this was actually trained on real data. This was basically, it was copying the paper used here to train it on some real data. And the moral of that story was LSTMs take a really, really long time to train unless you have beefy GPUs. So if anyone, yeah.
So for this particular model, you need to have like a set of answers that you're trying to pick from, essentially, or like it's not generating answers, right?
Right. Yeah. You have a sample set of answers. In this case, the loss function. You calculate embeddings for a good answer and a bad answer, and the loss function is you subtract the good answer and you add the bad answer, or the similarity between the good answer and the question, and you add the similarity between the bad answer and the question. So to make that go down, you want the similarity between the good answer and the question to go up, and the similarity between the bad answer and the question to go down. Or yeah.
So how does like have you seen the testing model on seeing questions and answers? Like how does it generalize, or is it basically just learning these particular combinations of questions and answers as well?
Oh yeah, no, it does generalize pretty well. Like you have a testing set. The data set here is like split into, there's like 3 different testing sets, and it got like in the paper it got like 60% top 1 accuracy, which is really good if you think about like all the possible answers. There's like 1 or 2 good answers, and it picked those out of 500 candidate answers. 60% of the time it gets the best one as its top choice. Yeah, I mean, I think there's been some work on like generating questions too. Yeah. So who's like, who thinks they'll use Keras at some point in the future? Nice. Hopefully, yeah, you can get involved with the Google group. There's like a pretty active community on there, and yeah, that's more or less it.
I just wondered if Keras was being used for any of the generative modeling research.
Yeah, a lot of it, a lot of the stuff that's going on right now is kind of starts with Keras because it's really easy to get your model up and testing it. So to be able to modify Keras to do stuff you want to do is really important, because if you want to try a new network, it's a lot easier to have all the basic stuff down so you can just try the interesting stuff. The generative stuff, like there's ways to do it in Keras. Like you basically set up this kind of network where you generate a sequence. It's pretty easy to do. So. The generative adversarial networks is hot right now. There was someone who wrote an implementation of that in Keras. Yeah, it's not in this repository, but other people have it for sure. I mean, yeah, it's a very popular framework right now. I think behind TensorFlow and Caffe, it's the most popular way to do deep learning, and it's a lot easier than either of those two, in my opinion. So.